Blackbody radiation and quantized energy. At the start of the 20th century, the understanding of the physical world was changing rapidly. The electron was discovered. There was evidence that the atom, which had been considered to be the smallest particle of matter, had an internal structure. Cathode rays were found out to be particles, gamma radiation was discovered, and the distinction of ray-like properties in solid matter blurred. Next, the very nature of light was to be challenged. All objects emit electromagnetic radiation, which depends on their temperature, thermal radiation. A black body absorbs all electromagnetic radiation that falls on it. Because no light is reflected or transmitted, the object appears black when it is cold. However, when black bodies are heated, they emit a temperature-dependent spectrum, termed blackbody radiation. The spectrum only depends on the temperature of the object. It doesn't matter what the material is. At normal temperatures, we're not aware of this radiation, as it's in the infrared part of the spectrum. But as objects become hotter, we can feel the infrared radiation or heat. At even hotter temperatures, the radiation moves into the visible spectrum and objects glow red. At still hotter temperatures, objects will glow white-hot, such as the filament in a light bulb. Wilhelm Wien, through experimental observation, determined the following equation that related the color of the light to its temperature. This is Wien's displacement law and shows that the higher the temperature, the shorter the wavelength of the peak color of the light. As an object gets hotter, it changes color from red to orange to blue, then finally to white. All wavelengths are present in high intensity in the visible spectrum. The graph shows blackbody radiation intensity as a function of wavelength. Actual data are plotted for three temperatures of a blackbody radiator: 3000 Kelvin, 4000 Kelvin, and 5000 Kelvin. The black curve at the right is for 5000 Kelvin and is predicted by classical physics theory according to the Rayleigh-Jeans law. K sub b here is the Boltzmann constant. The peak intensity of the light shifts from the longer wavelengths down to the visible spectrum, where it starts as red light, right here, and then moves to yellow, and then finally at 5000 Kelvin, all the colors are present. We get white light. At long wavelengths, the Rayleigh-Jeans law fits the data, as at larger wavelengths the intensity approaches zero. But it totally fails to match the data at short wavelengths, in the ultraviolet part of the spectrum. The predicted intensity approaches infinity, but the measured intensity actually approaches zero. This is known as the ultraviolet explosion. Because of this tremendous discrepancy between classical physics theory and reality, a revolutionary and not easily understood new idea was needed to match the observed data. The classical theory of light, based on a wave model, could not explain the intensity of the light as a function of the wavelength. The theory allowed the radiation to take on any value for the energy due to different wavelengths. So as the wavelengths became smaller, the intensity of the radiation approached infinity. In 1900, Max Planck made his brilliant assumption that atoms do not emit electromagnetic radiation with any continuous value. They could only emit in multiples of small distinct amounts of energy, called quanta. Planck's key principles were that the radiation comes from atomic oscillations in the black body. The atoms are excited to higher energy levels by the incoming light. When they return to their lower energy levels, they emit blackbody radiation. Also, only certain energy levels of the oscillations are allowed, and they are integral multiples of the frequency of the emitted light. The quantized energy levels are E equals NHF, where N is an integer and H is Planck's constant, which is a very small number. The energy of one quantum of radiation is equal to HF, where F is frequency. Using the quantized energy levels mixed with the probability of the quanta reaching specific energy levels, Planck came up with this equation for blackbody radiation. The exponent term made the equation approach zero as the wavelengths approached zero and infinity, and peaked somewhere in between. By adjusting the value of h, this equation matched the experimental data exactly. Also, for long wavelengths, Planck's expression matched the Rayleigh-Jeans law, which is good as that law also worked for long wavelengths. These quantum amounts are given by the following formula: E equals hf. This equation is on the AP Physics 2 equation sheet. E is the energy of the light, h is Planck's constant, a very small number, and f is the frequency of the light. Planck didn't believe this was real. It just worked. It was like working from the answers in the book, getting something that works but having no idea why. It didn't make sense that atoms could only have steps of energy. Why couldn't they have any energy? Planck thought a real solution would eventually be found, but this one just worked for some reason. Planck continued his analysis to try and make h equal to 0. If he could show that h was equal to 0, he could get rid of this notion of quantized energy levels. However, he didn't succeed, because it turns out that h is a fundamental constant of the universe, and numerous measurements made by other physicists confirmed it. This now leads to another mystery of the physical world that would be worked on by Albert Einstein and would use this quantum theory. It is the photoelectric effect. In atomic physics, energies are so low that it's awkward to use joules. A smaller unit of energy is the electron volt. Its value equals the potential energy of an electron in a region of space where the voltage is 1 volt. So if potential energy equals QV, Q is the charge of an electron, which is 1.6 times 10 to the negative 19th coulombs. The voltage is 1, so therefore 1 electron volt is equal to 1.6 times 10 to the negative 19th joules of energy. Planck's constant is also given in electron volts on the AP Physics 2 equation sheet. So h in electron volt seconds is 4.14 times 10 to the negative 15 electron volt seconds. What is the energy of a photon with a frequency of 5 times 10 to the 18th hertz? Remember, a photon is a particle of light. It is truly as simple as just plugging in values into this equation. So Planck's constant in joule seconds, we have frequency in hertz, which is 1 over seconds, right? So the seconds cancel, leaving us with an energy of 3.32 times 10 to the negative 15th joules. So just make sure that you are in the correct units. A photon has an energy of 4.2 times 10 to the negative 19th joules. What is the photon's wavelength? All right, so here we're going to combine the energy equation with the speed of light equation. So we have E equals hf. We also have F equals c over lambda. So we're going to take that c over lambda and plug it in there for frequency. That gives us E equals hc over lambda. By the way, both of these equations are on the AP Physics 2 equation sheet. So you combine them, solve it for lambda, plug in our values, and we get 472 nanometers, which you could look up on a chart and figure out what color light that is. What is the energy of a photon with a wavelength of 750 nanometers? All right, so the first step is to derive this equation. We have E equals hf. We also have lambda equals v over f. But remember, when light's traveling through a vacuum, the velocity is c over f. So solve this for f, and we get c over lambda. Plug this in for frequency there, and we get this. Next, we're going to plug in all of our values. Now, don't forget that if the wavelength is 750 nanometers, that means times 10 to the negative 9th meters. Plug it in, and we get 2.65 times 10 to the negative 19th joules of energy. What is the frequency of a photon with an energy of 4.5 times 10 to the negative 18th joules? All right, we want frequency. We have energy, just use this equation. Solve it for frequency, plug in our values, and we get 6.79 times 10 to the 15th hertz.